Thanks for having me. Thanks everybody for coming. So I want to talk about how we can use programming systems to build better systems for processing and learning about visual data. And most of what people focus on when talking about array and tensor languages today is machine learning. And indeed, driven by huge corporate investment, there's been an explosion in the amount of compute used to train state-of-the-art machine learning models over the past decade. But machine learning is just a small part of what we do with visual data. And visual computing is central to most of the ways we use computers today, both including ML and otherwise. And this is not just in games, movies, and cameras, but also in everything from robots and self-driving cars to mapping the world to engineering and design, 3D printing, science, and medicine. We almost take for granted that computers are visual tools today. But as successful as it is, visual computing has an almost unlimited demand for more performance and efficiency. It looks, basically just like that ML graph over the last many decades. So in rendering, for example, even using the same GPU as a PC game, a movie frame is still 6 orders of magnitude from real time. On the internet, basically all the biggest data is visual. So by 2015, YouTube was already ingesting over 400 hours of new video every minute. And today it's a significant multiple of this again still. But even that's just a trickle in the sea of active cameras, from medical scanners to smartphones to gigapixel telescopes. And we're developing powerful techniques to analyze this data, but they're really expensive. So running one large state-of-the-art object detector can take a large GPU just to process sub-VGA resolution video in real time. Now, in general purpose computing, I think a combination of new languages, libraries, and systems have driven programmer productivity through the roof over the past few decades. But the kinds of high performance implementations that these visual computing problems need are arguably harder than ever to build today. So for example, a recent algorithm added to Photoshop is pretty easy to describe in a couple hundred lines of code. But to get it into production, one of the best engineers at the company had to spend 3 months re-implementing and optimizing it. And the end result does the same exact computation, an order of magnitude faster, but it needs code that's at least an order of magnitude more complex. So my group's research, and a bit of what I want to talk about today, is how we can make this easier. So overall, we build systems, architectures, languages, and algorithms for these kinds of problems in visual computing. And specifically, we've worked a lot on high performance image processing for computational photography and vision, 3D graphics systems from offline and real-time rendering to simulation and 3D printing, and most recently at the interface of machine learning and systems. And that includes both the application of machine learning to optimizing systems and new programming systems that broaden where we can apply machine learning, especially for vision and graphics. And throughout this work, one of the big themes we've found is that the key challenge is often to reorganize or restructure computations and data. That our ability to do that is deeply connected to the dependencies in a given problem. And that to make progress, the key insight is often to use some kind of domain knowledge to define abstractions that help us structure the possible dependencies in organizations. And then by changing how we build systems from applications down to hardware using this idea, we can enable radically simpler code and more efficient systems and hardware in the twilight of Moore's law. All right, so how can we increase the performance and efficiency of apps like these? One of the challenges we face is exposing more and more parallelism for our hardware to exploit. So, superficially, this might seem easy. All the applications I talked about are enormously data parallel. And it's actually the fact that we have millions or billions of pixels, objects, neurons, or finite elements that makes us care about performance in the first place. But the real challenge, I think, is that these millions of data parallel computations are not independent. So they have to be able to communicate with each other. And the same hardware trends that have pushed us from one to many cores have made communication and data movement dominate the cost of computation. Now, by communication here, I don't even mean over networks. I mean inside a computer and even inside each chip. And as a result of that, locality, or moving data around as little as possible, is at least as big a problem for our programs today as parallelism. So today, to put this in concrete perspective, relative to the energy cost of doing some arithmetic operation on a piece of data, loading or storing that data in a small local SRAM like a cache can be several times more expensive. Moving the result 10 millimeters across the chip is an order of magnitude more expensive. And moving it to or from off-chip RAM is 3 to 4 orders of magnitude more expensive than computing the value in the first place. And this disparity is just getting bigger over time. Now, because of this, it can often be most efficient to make surprising trade-offs, like redundantly recomputing values that are used in multiple places instead of storing and reloading them from memory. And that's the first key message I want you to take away from this talk. We'll see this in a little more detail in a second, but parallelism, locality, and the total amount of work performed often interact in complicated ways. And they often need to be traded off against each other to maximize the performance and efficiency of an application on a particular machine. Okay, so now, given these pressures, where does performance actually come from? We often think of it in terms of two factors, the hardware that we have and the program that we're running on it. But the competing pressures on locality, parallelism, and redundant work depend heavily on exactly how our program is mapped to the hardware. So the second key message I want you to take away from this talk is that because of this, you should actually think of a program often as two separate concerns. What I'm going to call the algorithm, or the fundamental operations that need to be performed, and then the organization of the computation, including where and when those operations are performed and where their results are stored and loaded. And the work I want to talk about today focuses on enabling and exploiting the reorganization of computation and its interaction with hardware and algorithms. And I'm going to show that organizing computation is key to the things that we need to optimize performance and efficiency, but it's also challenging because of the fundamental tensions between them. But ultimately, if we want to build exploit the best hardware that physics is going to let us build, I think we need to treat the organization of computation as a first-class issue. Looking back quickly at the Adobe code I mentioned earlier, it turns out the optimized implementation here does this exact same computation as the reference. It's just been organized differently. And it was finding that optimized organization that took 3 months of work. So as skilled as he was, the developer had to explore lots of different possible organizations to find what performed best. So using a traditional language like C, each of these organizations globally restructured all the code, mashing together hundreds of loops in different ways. And because of stuff like this, not only is this kind of optimization painful and expensive, but it breaks the modularity of the resulting code. So once we fused it together, it's almost impossible to reuse parts of this code inside a different pipeline. And even composing this whole pipeline into a different application might mean reorganizing it all over again to be most efficient. So, as much impact as it had in this one case where it was clearly worthwhile to spend all that effort, this kind of work has to be repeated again and again. So to address this, we've been working for the past decade or so on a new programming language called Halide. So Halide is a language for dense, regular data parallel computations, what today we often call tensor processing. And we've specifically focused on things like image processing and deep learning. And the key concept in Halide is the idea of explicitly decoupling the algorithm from the organization of its computation. So going a level deeper, to see what I mean by the organization of computation, I think it helps to look at an example. So if we want to do a simple 3x3 box filter as 2 3x1 passes, we could write some C++ code like this. It's just a series of 2 sets of loops over the image, where the first computes a horizontal 3x1 blur and stores in a temporary buffer. And then the second computes a vertical 1x3 blur of that to produce the output. Now, an obvious question we can ask about the organization is, what happens if we exchange the loops in each loop nest? A lot of compilers could say these are the same algorithm. This loop reordering is something that many compilers could do today, and it's easy because the operations within the loops are independent. It turns out it's also important. Because of poor locality, the column major order is at least 15 times slower than the row major version on my laptop. And this is just a trivial reorganization of the computation. Again, something compilers can generally do already. But Halide is all about taking this to the next level, starting from what expert programmers traditionally have had to do by hand. And the key thing there is going to be organizing across the two Blur loops, not just within each one. So this is a hand-optimized version of the same function. It's a mess, it fits on a slide, but I think it's arguably a pretty big mess, given that all we're doing is averaging 3 by 3 pixels. But it's another order of magnitude faster, near the peak throughput of this machine. So comparing it to the original, it's completely different in the simple breadth first loops we started with. The code uses different instructions, different data layout, deeper loop nests. It shares almost no code with the simple version. But all that's actually happened here is a reorganization to optimize for parallelism and locality. So in this case, the parallelism comes from distributing work across threads and from computing in 8 wide SIMD chunks on each core's vector units. But again, just exposing this parallelism is not the biggest challenge in optimizing this program. Just as important, and often a lot harder to think about or express, is locality. So here, the optimized code improves locality by computing each stage in tiles, interleaving the computation of tiles across stages, and keeping intermediate data in local buffers that never have to leave the cache. And without that kind of locality optimization, even a well-parallelized pipeline is severely bottlenecked by memory bandwidth. Now, this kind of optimization is hard, both for people and for compilers, because getting parallelism and locality requires transforming the program and data structure. So first, we have to worry about what transformations are legal. And even when we know something's legal, it can be hard to know whether it's a good idea. So those things that we wanted to optimize are often at odds with each other. And making the optimal balance can be subtle and complex. So just making a single heuristic guess, like most compilers would do when optimizing, we might actually wind up making our program 10 times slower rather than faster. And critically, libraries of optimized code don't solve this. And that's because no matter how much Intel and NVIDIA tune the assembly inner loops of their math kernel library or cuDNN, individually optimized kernels generally still compose into inefficient pipelines because they can't interleave stages for locality across function boundaries. So using traditional programming tools, reorganizing it for high performance like this fundamentally breaks code modularity and composability. So that's the core problem that we want to address. Now, I think the right answer here is to explicitly decouple the definition of the algorithm from the organization of its computation, which I'm going to call the schedule. So in Halide, the algorithm defines what values are computed for each pipeline stage, while the schedule defines where and when they're computed. So that makes it easier for the programmer to write algorithms, strips out lots of unnecessary details, makes it easier to compose them into pipelines. It makes it easy for either a programmer or a compiler to specify and explore possible optimizations. And then it leaves the compiler free to do the complex but deterministic work of generating fast code that implements the pipeline given a schedule. All right, so I haven't been great at stopping for questions so far, so maybe I'll pause here for a second before I dive into a little more detail if there are any questions that have come up.
Do feel free just to chip in if you want to ask something. I don't see any questions, so.
Okay, so let's dig into what I actually mean. So to start out, algorithms are written in a declarative functional style. So once we strip out the concerns of scheduling, the algorithm is just a series of functions from pixel coordinates to expressions giving the values of those coordinates. So these functions don't have any side effects. They can be evaluated anywhere in an infinite domain, and the required region of each stage gets inferred by the compiler. The execution order and storage are unspecified, so points can be evaluated in any order. And the results can be cached, duplicated, thrown away, or recomputed without changing the meaning. And the resulting code looks like what you see here for the 3 by 3 blur. So The first stage, blur H, is defined at any point xy as the average of 3 points in the input. And then blur V at any point xy is the average of 3 points in blur H. So relative to code you might be used to, notice that there's no loops, bounds, or mutable memory buffers here. It's just a declarative specification of how to compute any point in any stage, including all of their fine-grained dependencies. And the specific scope of this programming model is what lets us understand the dependencies and have lots of flexibility in scheduling. So first, we're only modeling functions over regular arrays or tensors. Second, it focuses on feed-forward pipelines. So that's a good fit for imaging and vision, but not for everything. It can express limited recursion and iteration, but basically only countable loops, which is one of the ways we keep the analysis of these programs tractable. So that means it's actually not Turing complete. And then finally, our applications are made up of large graphs of heterogeneous computations. So we're not just interested in one iterated stencil or one small blur kernel like we saw, but the real programs we want to optimize are often 100 different stages or more with complex and varying dependence. And we potentially need to schedule them all differently to globally organize the computation. Okay, so we have this nice constrained functional model for expressing image processing algorithms. So now how can we organize it? And this is the real key to Halide. And I'm going to introduce it in 2 steps. So first, I'm going to use the blur example to sketch a theory of the problem and its challenges. And then I'm going to show how we applied this to build a model from which we can actually generate code. So I think it's easier to start to understand the organization of computation if we look at it as data flowing through a pipeline. So for our simple blur example here, the execution of the pipeline looks like this. I've reduced it to 1D, but all the problems are still the same. So the input image is at the top, flowing down through the blur H and blur V stages below. And then I'm showing the actual pixels on the right. And again, we're going to use this to introduce a theory of the types of reorganization that we do in Halide. So what's most significant here is not what happens within each stage, but what happens across the stages. So the first versions we looked at execute each stage breadth first. They first compute every pixel in the first stage before computing anything in the second. And we can execute in parallel within each stage, but we've completely sacrificed locality. And that's because the first stage produces a whole lot of intermediate data before it ever gets used in the second. So it has to be sent far away and written to memory before slowly reading it back in. So here, locality is a function of the reuse distance along this red path we take through our computation. And we can improve locality by interleaving the stages instead. And that's what we usually call fusion. So this reduces the distance between where values are produced in the first stage to where they're consumed in the second. But importantly, it makes optimization now a global problem of carefully interleaving the whole pipeline. And for this type of program, the type of image processing, tensor processing program that we're interested in, I also ignored a really critical detail, which is that to see how we can interleave a computation, we have to look at its dependencies. So in this case, looking at 1 pixel of blur V, it depends on 3 neighboring pixels in blur H. But if we think about it, its neighbor depends on an overlapping set of pixels. And this is a fundamental characteristic of stencil computations, and it means that the pixels that we wanted to interleave during fusion actually depend on overlapping pixels further up the pipeline. And that winds us giving 2 basic choices for how to do a fused organization here. So first, we can interleave the 2 stages in a sliding window. And then after computing, say, the first 2 values in the first stage, for each new value computed, we can immediately compute the corresponding value in the second. So that has great locality, quickly switching back and forth between computing and consuming values, but it fundamentally requires interlocking the execution order of the 2 stages, which constrains parallelism. Now, another thing we can do is decouple tiles of pixels to keep the short reuse distance while also executing in parallel. But for this, we need to break the dependencies between them. Now, by removing the dependency, we can execute in parallel both within each tile of each stage and across tiles. So we can compute parallel tiles at the first stage, send them down, and immediately compute tiles at the second. So now we not only have parallelism, but we also get good locality from the short fixed reuse distance within each of these computations. But to get here, we had to make a different trade-off. So to break the dependencies in the algorithm, we had to duplicate the shared computations along the boundary, which introduces redundant work. And this is a key trade-off that experts make when hand optimizing this kind of code, but it's not something that's very easy for most compilers to consider. So this brings me back to that first message that I gave you, which was that optimizing performance requires fundamental trade-offs. So we saw that there's a tension between locality or reuse distance and introducing redundant work to break long dependency chains. We can trade off along this axis by varying the granularity at which we interleave these stages, using smaller tiles for better locality or bigger tiles to minimize the fraction of duplicated nodes along the tile boundaries. And there's also a tension between these and parallelism, which requires independent work within or across stages. And the second message I gave you is that these trade-offs are determined by the organization of computation. And so in this example, I've shown you that changing the order and granularity of computation can have a huge impact on performance. So in this visualization we've been using, these aspects of the organization are given by the red path we take through the computation. And then the algorithm defines the dependencies between the individual tasks. And this leads to another key idea, which is that the ways that we actually can reorganize this graph and the effect that each choice has on locality, parallelism, and the amount of work we have to do is a function of the fundamental dependencies in the algorithm. And this is also one of the places where a domain-specific programming model can make a big difference in ensuring that our compiler actually can analyze these dependencies precisely. So we have these choices, different ways we can organize the same algorithm. Now I want to give you a taste of the language that we define to model these choices. So in Halide, a schedule defines the organization of computation in a pipeline like this by specifying two main things. So first, for each stage, in what order should we compute its values? Remember, we're computing whole arrays for each function, so in what order should we compute points in this array? And second, when should we compute pieces of its inputs, or at what granularity? That defines the interleaving of evaluation between producers and consumers in the pipeline, which is going to determine the amount of fusion between the stages. So this is the model we use to describe the space of ways a computation can be organized. And effectively what we did was create a new language as part of Halide for modeling this space of choices. So different choices about the order within and across stages can describe all the types of organization I showed earlier. And then composing these choices in different ways for different stages spans the space of trade-offs globally for a whole pipeline. Now, the scheduling model within each stage is relatively simple. So you can apply all the classic transformations on perfect loop nests, like splitting, reordering, tiling, vectorizing, basically all the classic things you might think of. But I think it's actually this way that we model global trade-offs, the interaction across stages, that's the most fundamental idea in Halide's design. We do that by controlling the granularity at which the storage and computation of each stage gets interleaved. So the granularity with which we interleave computation determines how soon you use values after you compute them. On this axis, fine-grained interleaving provides high temporal locality, quickly switching back and forth between computing and consuming values. While coarse interleaving provides poor locality, computing a whole lot of values before using any of them. On the other axis, the storage granularity determines how long we hold on to values for potential reuse. So fine-grained storage only keeps values around for a short time before throwing them away. So that can cause redundant computation if they're needed again later. Well, coarse grain storage keeps values around longer to capture more potential reuse. So using the organizations we explored before, breadth first execution avoids any redundant work by interleaving the computation and storage at the coarsest granularity. But as we've seen, this sacrifices locality. So in the scheduling language, this is modeled, this interleaving choice is described by the simple code you see on the right. At the other extreme, full fusion interleaves the storage and computation of the two stages at very fine granularity. And this maximizes locality, but potentially introduces lots of redundant work where the stencils overlap. So we're throwing away the pixels that we computed in the first stage for each new pixel that we compute in the second. In this third corner, by setting the storage granularity to the coarsest level while interleaving the computation per pixel, we get a sliding window pattern. So this has high locality and it does no redundant work. But as we saw before, doing this requires constraining the order of execution, which limits parallelism. We need to synchronize these stages in order to be able to carefully reuse the intermediate results that we're computing with this fine-grained interleaving. Now, this gets more interesting when we think about how we can actually trade off along these axes from there. So tile level fusion trades off between locality and redundant computation, depending on the granularity of the tiles that we interleave. Or starting from the sliding window schedule, we can coarsen the compute interleaving to regain fine-grained parallelism within the enlarged windows at the expense of some locality. We can regain coarse-grained parallelism by performing sliding windows within multiple parallel tiles, introducing redundant work on the tile boundaries. Or we can combine all of these strategies to span the entire interior of the trade-off space. So even for a pipeline as simple as this two-stage blur that we've been looking at, we can express a basically infinite range of choices in how to organize the computation. So the top three versions of the extremes of the trade-off space we saw first, while the bottom three balance them in the different ways that I showed. And hopefully this comes across somewhat on Zoom. I can share a video of this later, if not, but this is a little taste of what they actually look like running. The different strategies are going to be best depending on the exact algorithms that we're using, the structure of the surrounding pipeline, and how they interact with the underlying hardware. And importantly, as we've seen in all the concrete examples we've discussed so far, the difference between two of these can be more than an order of magnitude in performance and efficiency. So this bottom left schedule turns out to be the same organization as the hand-optimized C++ from before. And each of the others corresponds to a similarly complex but entirely different optimized loop nest. Now, making this one level more concrete, what the schedule actually does is define a loop nest to compute the whole pipeline. So given the simple blur algorithm, we first decide in what order to compute the values within the blur V stage. Oops, sorry. So we're first going to be looking at the blur V stage and thinking about what order we're computing values. So for example, we could compute it in 32 by 32 pixel tiles, which we can say in the scheduling language with a directive like this. That corresponds to a 4 deep loop nest over the domain of blur V, first iterating over each tile, and within that, iterating over each pixel. Then we have to decide at what granularity to interleave the computation of the earlier stage, blur H, within the computation of blur V. And in Halide, we do this by specifying the level in the loop nest of the consumer at which to compute the required values of the producer function. So here we can choose to compute blur H as needed for each tile of blur V. And that's here in the loop nest. So we're naming the granularity at which we want to compute by specifying the level in the loop nest at which we want to perform this computation. That injects a new loop nest to compute the required block of blur H at the corresponding point in the computation of blur V. And we can also do, all the extra stuff you might imagine, changing the loop nest of each function to do things like evaluating them in parallel or computing them in SIMD vectors. So putting this all together to describe an optimized blur looks like this. So this is the same algorithm from before, annotated with the schedule equivalent to the optimized C++ from the beginning. And this generates nearly identical machine code to the C++, but with just 2 lines each of algorithm and schedule. So unlike the C, the Halide version makes it easy to add new stages, change the algorithm, or change the organization. And it can also compile not just to x86, but to fast ARM Neon code, or with a few tweaks to the schedule, we can express a range of implementations for GPUs, DSPs, or different kinds of specialized accelerators. All right, so maybe I'll pause one more time for questions if anything's come up.
Are there any questions? It's all very clear.
Excellent.
So there is a question from Martin Elsman. Is there always a default schedule?
Great question. Is there, there is, the way the language is defined, the default schedule effectively corresponds to inlining every producer into its consumers, which, if you think about it, in many cases is actually pathologically bad. That was a design choice we made early on, because frequently when you break a program up into lots of small stages, one of the core things you want to do is have many of those stages get fused together. You don't want to have a performance penalty to every time you factor a computation into subcomponents. You'd be implying a pass-through memory if you didn't fuse them. And so we thought, for performance engineers like us, when we were originally developing this, we'd make it very concise by not requiring you to explicitly fuse things. Things would be fused by default, and it's only when you wanted to not fuse things that you would have to say anything. In retrospect, I think that was actually a questionable decision, because in the hands of less experienced users, it tends to mean that the default schedule they start out with blows up in their face. Because if you have a sequence of stencil dependencies like this, you're doing the maximum amount of redundant recomputation by just inlining all the producers into their consumers. So there might be more sensible default schedules today. It's a little bit difficult to change once things are used in production. But yeah, great question.
Another question from Vinod Grover. How does Halide handle irregular data shapes?
Great question. So I'm not touching on more advanced details of the language here. There is functionality for specifying more complex iteration schemes within a given one of these stages. So there's sort of a bounded notion of imperative updates that you can do within the definition of one of these stages. And within that mechanism, you can specify kind of arbitrary iteration shapes. So you can iterate over a circle or a triangle or whatever kind of shape you want. In terms of irregular data structures, the core functionality here is just operating on dense arrays or dense tensors. And aside from tricks you can play to try to encode irregular data structures yourself into these and work with them, to a first order language is not designed to deal with irregular data structures at all. But yeah, great question. I'll talk a little bit about taking similar ideas to the domain of sparse matrices and graphs at the end.
Great. Another question from Amir Shekhar. Is there some form of type system for the schedule? Great question.
So no, there isn't. In this language, the checking of the schedule is basically done while the compiler tries to apply it. And so there is a notion of safety. We have done quite a bit of work since this to show that the compiler is actually able to provide this guarantee. Basically, the schedule can't, the combination of checks in the compiler and the design of the scheduling language are such that the schedule can't change the values that are computed, and it can't influence the memory safety of the program that results. So any schedule for a Halide program, in any different schedule you could write for the same Halide program will always either throw an assertion that that it's unable to run safely with the sizes of inputs you've given and things like that, or the parameters you've given at runtime, or throw an error in the compiler that you gave a malformed schedule, or it will execute successfully with no memory errors and produce the same values in the output array. Showing why that is and how that works is actually an interesting exercise. We have a paper draft of which is on arXiv that's under review these days, talking about how to think about that formally and what those, kind of what that meta theory of what a safe scheduling language is should actually look like. But in general, the guarantee is it's a bug in the compiler if changing the schedule can change anything, but it's not really a type style of checking.
Right, so you've already answered William Brandon's question, which was essentially about safety. Baba Khan asks, is there a way to automatically schedule line buffered pipelines?
Great question. We will come back to that at least a little bit later. I won't be going deep on line buffer pipelines specifically, although we can talk more about that at the end. I cut that portion out for time, but I'll be talking about automatic scheduling in general in a second.
Great, all excellent questions. If there are no more, then do proceed. Okay.
So important thing I want to highlight is that this Blur is just a trivial two-stage pipeline. So this, main program we've been looking at is kind of the smallest thing that exhibits any of the interesting effects we're interested in. And a more realistic pipeline looks like this. So local Laplacian filters has about 100 stages in a complex graph. Locally, most of the dependencies are simple, like in our Blur, but globally, they're extremely far-reaching and complex. And that ultimately gives us lots of choices about the organization and degree of fusion in each of dozens of stages. So each strategy here can mean totally different sets of dozens of kernels or loop nests, completely restructuring all our code. And the difference between two plausible strategies can be an order of magnitude in efficiency. So to put this in concrete perspective, this algorithm, local Laplacian filters, is that algorithm we saw at the beginning in Photoshop. Remember, Adobe's version was written by one of their best engineers in about 1,500 lines of optimized C++. It's multi-threaded and hand-coded for vector execution, and it took them about 3 months to implement and optimize. Just like our Blur example, the optimized version is 10 times faster than a clean version written in about 300 lines of C++. Again, because it's been globally reorganized for parallelism and locality. In comparison, a number of years ago, I sat down with him and we were able to take a single day to rewrite their version in Halide and integrate it into Photoshop. It took, 60 lines of code and ran twice as fast as their version on the same machine at the time. Now, everybody likes to trumpet, speed up numbers over impressive baselines, but I'm actually usually skeptical when people beat hand optimized like existing established high performance things. So, what was going on here? How did we actually beat this expert tuned code? And the win here came mostly from fusing stages to different degrees and accepting some redundant computation in exchange for better locality. But the Halide implementation didn't just make a couple extra optimizations. It actually had to fuse and schedule each of these 100 stages differently to globally balance parallelism, locality, and the total amount of work over the whole pipeline. And basically, what happened here is that the best organization of computation was just too hard for the original developer to find. So he stopped after 3 months of reasonable effort, rewriting and optimizing for one machine. But with Halide, it was orders of magnitude easier, exactly because of the scheduling language and the guarantees it provides, to globally reorganize this computation. So as a result, in that one day, we were able to try lots of different stuff and ultimately find something more efficient overall in a few hours of work. At the same time, Adobe wanted to use GPUs for this kind of code, but couldn't afford to rewrite thousands of lines for each accelerator. But in just a few more minutes, just changing the Halide schedule further, we also generated a GPU version that was 10 times faster still. And importantly, this wasn't just a translation. The best schedules on these different architectures organize the computation in totally different ways. So today, different versions of this code are also in Instagram and Google's HDR+ using different schedules to target a wide range of different accelerators. Now, to implement real applications like this, we touched on this a little bit in the questions, but Halide has a bunch of language features beyond the scope of what I showed so far in this talk to represent things more complex than simple stencils. But I generally recommend checking out the papers or these days the open source project and documentation for more. Using all this, local Laplacian filters is also just one of dozens of applications we've explored in the published research and open source code. We'll skip over this quickly. I recommend, again, checking out the, for current state of the art, checking out the open source project in its current form. Higher order bit is that we find for the types of programs that fit well into this model, Halide can consistently deliver state-of-the-art performance with dramatically less code. And in every case, I also want to emphasize, any performance advantage over prior hand optimized code comes not from some compiler magic or because we were cheating with the baseline, but just from being able to find better organizations more productively and more easily. All right, so that's the core of Halide. To recap, the big idea was to explicitly decouple the definition of the algorithm from the organization of its computation, and to define a structured language of key scheduling choices. The end result are simpler programs that often run faster than traditional hand-tuned code while giving composable and portable components that can scale from embedded DSPs to supercomputers. And it's being used pretty heavily in the real world. So it's in Photoshop and Instagram and lots of other things, from pretty much every Android phone to most of the videos processed by YouTube. So in YouTube alone, last I knew at least, it accounted for a non-trivial percentage of all of Google server CPU cycles worldwide. And the performance improvements here eliminated megawatts of data center capacity. So overall, there's Halide code running in production on billions of devices, including probably most of the phones in your pockets right now. All right. So now I want to talk a little bit about more recent work we've been doing building on top of Halide at the intersection of machine learning and systems. And first, I want to talk about how we can use machine learning to optimize the performance of our systems. So can we automate the kind of performance engineering that traditionally needs to be done by human experts? And second, I'll touch briefly on how we can broaden the applicability of how we might be able to broaden the applicability of machine learning techniques. So specifically, how we can use gradient-based optimization to make more general programs learnable. And how we can use learning systems in contexts where large, deep networks are just too expensive. Now, there's obviously lots of interest in applying machine learning to everything, including systems, but the sorts of performance engineering usually done by human experts requires precisely navigating very complex spaces of possible choices. And there's highly nonlinear behavior in how these choices impact performance. So the kind of structure I've been talking about, like the structured organization of computation in Halide, I think is critical to leveraging learning in this context. And that's because it enables the combination of learning with powerful program analysis and search techniques, where each one is insufficient on its own. So using this idea, we've been working on learning to automatically schedule arbitrary Halide programs better than the best human experts. And we're also working on systems that broaden the scope of deep learning techniques and make it easier to achieve high performance. By creating a programming language that's both differentiable and efficient, we can, on the one hand, use learning techniques to better optimize the internal parameters of traditional programs. And on the other, build new neural network layer architectures or even entire networks with a more general computational model. So in a sense, we're both bringing more general computational models to deep learning and bringing deep learning to more general programs. So first, how can we optimize programs? So performance engineering is hard. Traditional heuristic-based compiler optimizations are great, but they aren't nearly as good at humans at the sort of large-scale reorganization that gives the order of magnitude wins I've been showing. So lots of people are hoping that learning will help compilers do better. But I still think it's an open question how we can learn to optimize programs. So with Halide, we defined a structured language of schedules, which describes most important optimizations. And we also have a growing mass of real expert-tuned code used in production. So The first thing you might think is maybe we could train a system to directly predict fast schedules for a given algorithm. But I actually think this is throwing the baby out with the bathwater. The space of schedules and their performance is incredibly complex, but it's also highly structured. So instead, I think that the right approach here is, or at least one very promising approach that we've been exploring, is to combine the strengths of structured search algorithms from classical AI, program analysis from compilers, and learning. And then we can focus the learning on predicting the best policy to guide the search, given everything we can infer about the program from classical analyses. At some level, you can think of this sort of like AlphaGo, but for optimizing programs. And this is exactly what we've been doing over the past few years. So with this new auto-scheduling system we've been building, we train small deep models to predict the performance of thousands of random programs and schedules on a target machine. Then we use that model to guide a beam search over a structured enumeration of possible schedules. And we can either find a schedule directly in a few seconds from this search, which you can think of like -03 in GCC, just the take a program, make it go fast mode. Or if we have some more time, we can import and sample the space of schedules favored by the model, benchmark the top results, and add a final layer of auto tuning. And that's useful if we have a few minutes to a few hours to wait for better results. And the punchline is that this works really well. So this is the first automatic algorithm that consistently outperforms human experts on a wide range of real image processing, graphics, and learning workloads targeted by Halide. So across a diverse benchmark suite of a couple dozen different interesting programs, it essentially matches human experts in that instant -03 mode and outperforms them by 40% on average, given an hour of auto tuning time. And sometimes it's an order of magnitude faster. We've applied this to machine learning workloads also with some pretty compelling results. But I'm going to skip over that for now. Then on the other side, starting from Halide, we've been building a fully differentiable programming language. So modern ML frameworks like PyTorch and TensorFlow are great for traditional deep learning. As long as what you want to do is well described by the standard layers they provide, they automatically give you both efficient GPU implementations and derivatives for gradient-based optimization. But the frontier in deep learning often involves extending traditional architectures with new differentiable operators. And that can be the key to capture problem-specific structure and make learning practical and efficient for a given problem. So the fixed library of coarse-grained operators in these traditional frameworks makes it difficult or impossible to express many new operators. The result's often fundamentally inefficient since it can't reorganize computation across operator kernels. The only alternative is usually to hand-derive gradients and manually implement it all in CUDA. But by balancing generality and structure, our differentiable programming language is both faster and more general than PyTorch or TensorFlow for defining many of these kinds of novel architectures. And it's orders of magnitude easier than having to handwrite and differentiate CUDA. That makes it much easier to define novel architectures for deep learning, but more surprisingly, we've also shown how you can use it to take traditional programs, learn more optimal parameters, and get deep learning level results. So for example, AHD is a state-of-the-art classical demosaicing algorithm like the one still used in your camera today, but it's been surpassed dramatically by deep methods in the last few years. But just by taking the same loss function and training data and using them to resolve for the optimal parameters of the classical algorithm, we were able to dramatically improve its performance, approaching the best deep models. But this learned classical program uses literally 1,000 times less compute data than the continents. And once the parameters of the whole algorithm are automatically learned, it's also easy to explore a whole space of new variants. So we can throw in things like larger or smaller filters in different places to trade off performance and quality. And doing this is relatively effortless with a differentiable programming language. So we're blurring the boundary between deep learning and more general programming. All right, so in the interest of time, I'm actually going to skip ahead to the end. Sorry. and just pop up to recall, the main theme we've touched on here, which is using domain knowledge in graphics and visual computing to model and analyze the dependencies between data structures and computations in different applications, and how using this to build new languages and compilers that explicitly deal with the organization of computations and data can help us balance competing pressures for locality, parallelism, the total amount of work performed, and build simpler programs, faster systems, and more efficient hardware. Looking forward, building on this recent differentiable programming result, I think points towards a whole new way to approach learning for efficient inference, especially for performance critical tasks like real-time imaging and video. So we've been working for the last couple of years investigating learning to solve these tasks by combining program synthesis over this broader space of differentiable programs with gradient-based optimizations of those programs parameters, and have some really promising initial results there. So in some sense, you can think of the idea as, instead of relying only on the massive overparameterization of traditional deep networks, the resulting programs that we synthesize combine algorithmic structure with parameter tuning to solve tasks with potentially orders of magnitude less compute and weight data, like I was showing in the case of demosaicing. We're also thinking about unifying Halide's decoupled scheduling model for arrays and everything we've built around it with more general data structures using a relational perspective. And I think with that, I will wrap up since we're just hitting the hour and just say thanks. And I'm happy to take questions and talk further.